Newton's law of gravitation. So the statement of the law, um, the gravitational field of attraction, or the gravitational force of attraction, between two point masses is directly proportional to the product of the masses product of the masses and inversely proportional to the square of the distance between them. So this is the statement. The gravitational force of attraction between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance. Let's try to make it a little bit more clear. So we'll draw an image that will reveal the details. Here we have a body, and then we have a second body in here. These two bodies will be considered point masses. We will talk about point masses soon. Now this is the line joining the two bodies. Here we have. So the line is joining between the center of masses of the two bodies. Let's assume that this body has a mass capital M, and the mass of this body is small m, and the distance between the particle and the point masses is r. Then by Newton's second law, the Newton's law of gravitation, the force of attraction between the two bodies, the small m, this body will be attracted toward the first body, and the first body will be attracted toward the second body. These two forces will be equal and opposite, forming action-reaction pairs by Newton's third law. So the magnitude of the forces, we are not really worried at the moment about the directions. The magnitude of the forces, they're equal. So we can write this: F is proportional to product of the masses, that is m times m, and F is inversely proportional to square of the distance between the two masses, that is r square. So if you combine these two things together, you will get F is proportional to m over r square. Now we can change this proportionality into an equation by multiplying it with the constant. So you can just write the gravitational force of attraction between the two masses F is equals to G times M upon R square over R square. In this case, the proportionality constant G is called universal gravitational constant. Universal gravitational gravitational constant, and the G has a value G in this universe, as if you know many other universes, right? In this universe, as approximately 6.67 times 10 to the power minus 11. The unit can be easily worked out, Newton meter square upon kilogram square. So this is Newton meter square kilogram to the power minus 2. This is it. This is the value of G. You can see that the value of G is extremely small. So this is the reason why gravitational force is extremely small compared to the electrostatic force. You can just write that just as an idea, not a very important one. G is very small, the universe. Therefore, this is one of the reasons. Therefore, you can write gravitational force in general is much smaller than electric force. Just an idea, not very important at this stage. So, let's see some of the important characteristics of gravitation. Oh, before that, we should know what is point mass. So let's talk about point mass for a while. Point mass, all right. What does it mean by point mass? Because the Newton's law is applicable only for point masses. Point mass. So what does it mean by point mass? Now, listen here. A point mass is in fact any object or a body whose physical dimension is far less than the distances involved in considering the gravitational force. A body whose physical dimension physical dimension is far less compared to the distances involved, the distances involved, of course, involved in evaluating the gravitational force. So we'll keep it as distance involved to make it short. Distance is involved in evaluating the gravitational force. And when that happens, that we call extended bodies, as you have seen in the diagram, you can see that in such cases, okay, in such cases, so in case of extended bodies, in case of extended we assume that the whole mass of the body is concentrated at the center of mass. We assume that the whole mass of the body is concentrated at the center. So this is one of the reasons. So we can see that the gravitational force acts between the center of masses of the two bodies. This is a basic idea. So this is one of the important characteristics. So we'll see some of the characteristics of gravitational force. That's right. Properties of gravitational force. Properties of gravitational force. What are the various properties of gravitational force? We'll make it really short. Here we go. Most important characteristic. I can write this as always attractive. Gravitational force, as far as we know, is always attractive. Always attractive. Second point, gravitational force is central force. Central force. What does it mean by central force? It means that the force attract gravitational force acts along the line joining the two bodies. Two bodies. It's an important property. And the third important characteristic is gravitational force is independent of the medium between the bodies. It's very important. Gravitational force is independent, independent, is independent of the medium between the bodies. Between bodies. These are the most important properties. If I can think about any other uh, interesting points, of course, it's a long range force, which we have already discussed. Gravitational force is a long range force. So its force is, experienced even far away from the object, as long as the objects are very heavy. Long range force. And if you want, you can add the other property as well. Fg, which stands for the gravitational force, is far less compared to the electrostatic force Fe. So these are some of the properties of gravitational force. You can see that always attractive. Now, let us look at the vector equations and the directions involved in the case of gravitational force. Take a look at this diagram again, and it's not very important for your exam, but better get the whole idea clear. All right. Suppose we have two masses again, and we have the line joining the two masses here. All right. Now, again, we consider this as, let's write this as M1 and M2 for the convenience. Would it help us a little bit? Maybe. Alright, let's write the masses as m1 and m2, just a matter of convenience when indexing is done. So the force experienced by the mass m1, let's write it as f1, is a vector quantity, and the force experienced by m2 due to the attraction of m1, let's call it as f2. And then suppose we consider the f2, the force on the second body due to the first body. Let's put the vector signs. The force will be f2 is towards, and this is the distance from r1 to m1 to m2. We call it as r1. m2 to m1, which is exactly the same magnitude, we call it as r2. So the relationships are pretty simple. Vector f1 is equal and opposite to vector f2. Of course, vector r1 is equal and opposite to vector r2. So both will have the same. So you can write the magnitude of both these quantities like this. Vector f1 is magnitude is equals to vector f2 magnitude. Let's write as f. And similarly, we can write vector r1 magnitude of vector r1 is equals to, we can see it from the figure itself, magnitude of vector r2. Let's write it as r, and then we may probably write the whole equation with the signs represented by the directions represented by the sign. For example, we may write, in case of f1, the magnitude of f1, which is actually force on, force on m2 due to m1 can be written as, because in that case the r1 is applicable, so f2 and r1 will be in opposite direction. In this case we can write f2 is equal to g m1 m2 over, I must remember the direction is towards, so you'll have, what will be the direction? Minus r1, minus r1, right? So because the division by the vector is just, kind of irrelevant, so we will do the vector part here. We write it as r1 hat. So it's opposite direction of r1. So you will write this as, without removing all the vector notations, we can just write f2 is equal to negative of g m1 m2 r. And now this negative sign in here, implies only that f2 is opposite to the direction of r as measured from the source. What is it? f2 is opposite to the direction of r as measured from the source, because this will be the source. I hope you understand it, and even if you don't get it clear, there are better ways to do this using position vectors. You may try it out, refer to some of the textbooks and you will find it, or you can contact me and I will explain it later. So this is about gravitational force between two point masses. Now suppose you have a large collection of point masses, and remember that there is nothing like point mass we are talking about. We can use any extended body as point mass as long as the size of this extended body is far less compared to the distances involved in the evaluation of the gravitational force. So we will have superposition principle. Let's put in a different color, maybe for the fun of it. superposition principle. I'm sure you're familiar with this idea before because we have seen it in wave optics. Superposition principle. This will help us calculate gravitational force due to multiple point charges. That's advantage. Now, what does it say? There are different ways you can describe this, but the idea is very simple. Is that if you want to calculate the net gravitational force, net gravitational force the net gravitational force on a point mass is equal to the I'm sorry, we need to add a couple of ideas in here. The net gravitational force on a point mass due to several other point masses is equal to the vector sum of the gravitational forces due to each of those masses each of those masses I should make a spelling each of those masses taken separately. So let's see what exactly it is. Though it sounds pretty complicated, it is a very simple idea. Take a look at here. Suppose you have several masses. I'm just going to draw several masses in here. Okay, here we have one. Doesn't matter. They may have different sizes. So it doesn't really match actually. Let's assume that we call this, let's assume that this mass is M, and let's call this M1, M2, and M3. So if you want to find out the net gravitational force on M due to all these different masses M1, M2, and M3, to find that out, you can draw the line joining all the three in pairs like this. These lines should be between the center of masses of the bodies. So we are trying to evaluate the force. All right, now let us see that, what is the force between force exerted on M due to M1, we can call it as F1, and force exerted by M2 on M, let's call it as F2. Of course, these are all vector quantities. So we will put the vector sign on top. And the force on M3, let's call this as M3. Sorry. So M3 is given by F3, vector F3. In this case, the net force on M, now it's very simple. Net, nothing complicated in here. Net gravitational force on M, let's call it as vector F, that is equals to vector F1 plus vector F2 plus vector F3. Now, So this is the actual technique to work out the net gravitational force on a body due to different other bodies. Let's do a simple example. Here you need to add them as vectors, just remember that. So let us have this particular picture. All right, I'm going to draw a diagram. Let's say we have, all right, an equilateral triangle. You know the meaning of that? It means all the three sides are equal and the three angles are equal to 60 degrees each. You call it equilateral triangle. Okay, let's see. And let's assume that we have masses in here. Let's say we'll just put some actual values to make it interesting. Let's say the value is irrelevant, you know, how significant this value. Let's assume that this mass we call it as m1, that's equals to, let's say, 2 kilogram. Okay, these are too small to actually create any real gravitational force. You must remember that. Let's assume that this is a very small body. So here we have the second body, right? Let's call it M2, and we have a third body. Let's call this M3. Okay. So this is M2. Let's assume that there is 5 kilogram, and let's see, this is M3. Let's take this also 5 kilogram. Now let's find out the net gravitational force on M2. So the question is, let's say this distance, all the three sides are, let's say, 1 meter, 1 meter, 1 meter. Now I want you to evaluate or find the magnitude and direction of the net gravitational force, direction of the net gravitational force. This is not an important question. Net gravitational force or mass m1. You can try this out. This is not very important. I just thought of giving you an idea of superposition principle. That was the only intention on this. So we'll stop it here for a while and then we'll have another lesson.